Okay, welcome. You're our final presentation for the day. So you're gonna have 15 minutes to present. I'll give you a 5-minute, a 2-minute, and a 1-minute warning. And then at the end, we'll have about 5 minutes for questions, and you'll have a chance to thank your coaches or families or whoever you want to thank. So whenever you're ready, you can get started. We just ask that before you start the presentation, please introduce yourselves by name. And then when you start the actual presentation, I'll start the timer. Go ahead.
Hi, I'm Jack Dunn. I'm a senior.
Hi, I'm Divya Kudva. I'm a junior.
Hi, I'm Kevin. I'm a senior.
Hi, I'm Billy. I'm a senior.
Hi, I'm Neve. I'm a senior.
And we're Team 17839 from Flint Hill School, and we are presenting our solution to the hot button issue, staying cool as the world heats up.
My team and I have two major worries. Our first concern is with the systemic threat that heat waves pose to urban residents across the United States. A report from NPR showed that less affluent neighborhoods of urban areas are disproportionately affected by heat waves. Additionally, a climate check risk report on Memphis, Tennessee predicts that by 2050, the city will experience 51 days per year with over 96-degree Fahrenheit temperatures. We've chosen the given data from Memphis to further understand the threat that heat waves pose to urban residents and to determine how to reduce the drastic impacts of climate inequality. The first problem asks us to develop a model to predict the indoor temperature of urban residences without AC. Our model is based on a few key assumptions. First, we established that the general approximation of a singular floor of a house is 10 feet. Another intuitive decision we made was that older houses have worse insulation, and that must be accounted for in our model. Third, we needed a standard value for air change rate of houses in Memphis, which represents the amount of times the air of a dwelling is replaced by outdoor air. I'll soon explain how this factor is used in our model. Our model considers thermal capacity, which we approximated to be 75,000 joules per Kelvin. Finally, we must assume that the heat source from the sun onto a housing unit is 3 degrees Celsius and only lasts from 6 a.m. to 6 p.m. Otherwise, this additional heat is 0 degrees Celsius. For our model, we decided upon a general energy balance equation. This will allow us to take into account several different sources of thermal energy using the data on dwellings in Memphis. In the form of a differential equation, we can solve for the rate of change of internal temperature of a housing unit. This easily allows us to model the temperature of a dwelling over a 24-hour period and thus allows us to estimate the effect of a heat wave on urban residences. This is the formula for the differential equation of an energy balance equation. We are able to define several sources of heat and utilize separate equations for each Q variable. One note, however, is that we eschewed Q solar from our final equation due to the fact that solar radiation was taken into account with our formula for Q conduction. I'll now explain how we calculate each individual variable. Our first consideration is heat from conduction. This formula uses Newton's law of cooling, which in this context means that the rate at which internal temperature of a house changes is proportional to the difference in outside and inside temperatures. The equation uses UA, the constant of insulation, which we determined from building types, with apartments having better heat transfer and houses having a worse one. The TSA variable is solar air, which is the temperature outside plus a factor of solar radiation on the residence, determined from the given shadiness qualities. Delta T simply enumerates the heat added from direct sunlight, thus why we scrapped a Q solar variable. Q internal is quite simple, in which we consider the number of people inside a residence and multiply that by the heat generated by a human at rest, which on average is 100 watts, relying on the assumption that all residents are within the house during this heat wave. Finally, Q ventilation determines heat gained or lost from circulation of outdoor air into the residences. We do so by considering an assumed rate of 3 air changes per hour, telling us at what rate indoor air is replaced. This is our final differential equation for question 1, with the defined heat energy equations for Q conduction, Q internal, and Q ventilation implemented. Here are results, with the graph showing the internal temperature of each of the 4 given residences over a 24-hour heat wave period, with the black dotted line showing the outside temperature in Memphis. Our findings show that home 2 was the most susceptible to the heat wave, peaking at over 42 degrees Celsius after sunset, primarily due to the old age of the unit as well as the exposure to the sun. Our model suggests that smaller residences, like homes 1, 2, and 3, retain heat to a notable degree, with homes 2 and 3 having particularly high retention of heat due to being apartments with worse insulation, which would trap outdoor heat within the dwellings for a prolonged period of time. Despite both being apartments, Home 2 has a slower rate of cooling compared to Home 3, likely due to Home 2 being an older unit. Home 4, however, faces greater extremes in temperature as it is susceptible to rapid overheating due to the full exposure to solar radiation, as well as having a high occupancy of 6 residents. Our findings suggest that the location and shade, size of homes, and number of occupants are crucial factors to consider when determining risk for overheating. Our energy balance model is incredibly effective in capturing the rate of change for internal temperature. Since we must understand the rate of cooling and heating of residences, it's beneficial that this model takes into account instantaneous temperature. Additionally, this model is largely intuitive in that every part of our calculations has a logical explanation. Compared to neural networks, our model is by no means a black box process, which makes it easily applicable to real-world scenarios. Unfortunately, our model fails to take into account variance in weather. Factors like wind speed and sunniness certainly affect internal temperature, but could not effectively be incorporated into our model. Another shortcoming is in our calculations, in which using Euler's method led our data to be discontinuous. Thus, our data is only a close approximation to the actual solution. Additionally, in order to use Euler's method, we had to interpolate the given data from hours into seconds, which may hinder the accuracy of our model.
Problem 2 asks us to develop a model that predicts the peak power demand that Memphis, Tennessee's power grid should be prepared to handle during the summer months. It also asked us if we foresee any changes in the peak power demand 20 years from now. In order to tackle this problem, we had to make a few key assumptions. Our first assumption is that the average temperature people in Memphis keep their houses at is between 70 and 73 degrees Fahrenheit. Secondly, we assumed that air conditioning units have varied capacity factors based on age, as it is effective in capturing the rate of, as it reflects real-world conditions where older AC systems experience reduced capacity due to outdated technology, and improper sizing. Thirdly, we assumed that buildings have a single thermal zone, as is standard for city-scale simulation. We also assumed that Memphis's housing stock can be represented by 4 archetypal building models, as considering all possible dwellings increases the complexity greatly. To tackle this problem, we decided to use a simulation model that utilizes our solution to question 1 to create a thermal equilibrium model. This simulation combines the power draw from dwellings due to air conditioning and a power baseline that accounts for appliances and other uses. To accurately model the entirety of the housing stock in Memphis, we created an age and type distributions for all the houses. The power baseline was created by averaging the power draw for the city of Memphis during the spring and fall months, as these months can be expected to have the least amount of air conditioning or heating usage. Building off our solution to question 1, we built a thermal equilibrium model quantifying the heat exchange between buildings and the environment. This approach offers an accurate citywide demand representation by calculating the energy required by a house to keep it at their desired temperature. Unlike statistical regression, our model captures nonlinear temperature-power relationships and accounts for crucial building-specific factors like insulation and AC efficiency, which historical data alone cannot provide. Our energy balance equation from question 1 tells us the amount of energy needed to keep a house at the set point. We then divide by a coefficient of performance for the AC unit, allowing us to relate it to the amount of energy it takes to cool the house to the energy increase inside the house. If this value exceeds the amount of energy the AC unit is rated for, the house's temperature increases, and the power consumed by the AC unit is the power it is rated for, multiplied by the capacity factor. Our simulation consists of adding the baseline of powers to the sum power draw from each of the 4 archetypal dwellings, with a scaling factor applied to account for industrial and commercial air conditioning. We then simulated a heat wave in Memphis, which showed a total power draw of roughly 2,850 megawatts, with 32.5% being from air conditioning. After running our simulation, we conducted a sensitivity analysis to determine what factors are most important. We reran our model multiple times, varying different constants to determine their effect on power consumption. We noted when we increased the AC efficiency, we noticed a decrease in overall power consumption. This is logical, as if the efficiency of AC increases, it would take less power to cool the houses. The sensitivity analysis also revealed that if the temperature set point was decreased, the power consumption would increase. These results provide us with insights into future changes for power consumption for Memphis. Due to rises in global temperatures from global warming and increases in the population, the maximum power draw Memphis will experience during a heat wave will most likely increase. While other factors such as zoning changes in Memphis, requiring better insulation and improved air conditioning technology, will help decrease the amount of power draw the city requires, the increase from rising temperatures and population growth will overall cause the power draw to increase. Our model effectively captures the essential physics of heat transfer and building thermodynamics, allowing for a more accurate power consumption due to air conditioning usage. It also helps capture the nonlinear relationship between temperature and power consumption, giving us insights into how different factors such as the age of the dwellings and shade affect the overall power consumption. One weakness is our model simplifies the diverse Memphis housing stock into 4 archetypal dwellings. Another weakness is that our model also fails to consider differences in the thermostat behavior across different dwellings.
For question 3, we were asked to create a neighborhood vulnerability score to equitably allocate resources during heat waves or power grid failures. And in order to do this, we made 2 key assumptions. First, we assumed that all houses built within the same decade share the same construction material and therefore offer same levels of insulation. And second, we assumed that the result of a vulnerability index reveal accurate insights into a resource index. To briefly go over a model for problem 3, we chose to conduct a principal component analysis, or PCA. PCA is a commonly used dimension reductionality technique that also has a secondary use case of determining weights. This second use is what we decided for our solution. This is better, as inspecting the weight of each variable on each component allows to quickly identify which original features drive the most variation, making the data more interpretable and meaningful. As for our methodology, we began by implementing our vulnerability factors into a standardized data matrix. Then we computed a covariance matrix for the standard data matrix and extracted its eigenvalues and eigenvectors. We then took the absolute value of the eigenvector entries, scaled them by the corresponding eigenvalues, and summed them to form a vulnerability weight factor, which we then multiplied by the standardized data matrix from before. This produces a weighted vulnerability value vector, which we finally then converted into a vulnerability index per location. We then use this vulnerability index and feed it into our list of resource factor and repeated the process again. This resource index is how we determine which neighborhood required the most aid in a heat wave or power grid failure. And these were the relevant equations we used, the top one being one for the weight factor, the second for the value factor, and the last one being the equations for how we convert the value factor into an index score.
The factors we chose to determine the vulnerability weight vector are shown above. This second use is what we decided. The factors which affected the vulnerability score the most are indicated by the length of the arrows above, with green being positive and red being negative. The most impactful factors are the number of households built in 2010 or later, and homes built in 1950 or earlier. This lines to reason as it's reasonable to assume that recent households are less susceptible to heat waves and older households are more susceptible. These are the factors we chose for the resource weight vector. The most impactful factors are indicated the same as before. It is important to note that this score also took into account our vulnerability score, which is determined from the vulnerability weight vector. This meant that the resource score not only included demographic factors on individuals in different neighborhoods, but also took into account how vulnerable a given neighborhood is during a heat wave. The 2 most impactful factors for this score are median household income and households with no vehicles. As indicated by the direction of the vector above, the more median household income has, the less resources they need. And if they have little to no vehicles, they will have a higher resource score indicating they need more resources. As for our index, our vulnerability scores were scaled from 0 to 100, with 100 being the most vulnerable and 0 being the least. Looking at the results, we can see that vulnerability, East Memphis scores 100, meaning this area likely faces compounding risks like poverty or environmental hazards. Conversely, Roseville, scoring 9.99, is not vulnerable during heat waves. Our resource scores were scaled from 0 to 100, with 100 needing the least resources and 0 needing the most. For our resource scores, Collieryville/Pipperton with a score of 100 has robust funding or infrastructure, so they will not be needing any additional resources, while South Forum/Washington Heights with a score of roughly 14 may lack critical services. Some strengths for our model are that no prior resource and vulnerability scores are needed, as PCA is built directly from current inputs. Additionally, PCA makes the standardization more objective due to the PCA makes the assessment more objective due to the standardization of data. Some weaknesses of our model are that feature ambiguity, where linear combinations of all the factors make it hard to isolate individual factors. Surface level analysis, while scores rank areas, they don't explain why components such as houses created after 2010 correlate with vulnerability. Deeper component breakdowns would improve actionability. To recap what we have previously covered, in Q1 we have the general energy balance equation, which is a differential equation stemming from Newton's laws of cooling. Temperature caused by body heat, temperature caused by ventilation, and temperature change due to the sun and radiation. In Q2, we utilized our peak energy consumption required equation, which was modeled using a simulation. This allows us to model the peak energy consumption required even if the relationship between the variables is nonlinear. Finally, for Q3, we have our principal component analysis, which allowed us to determine weights for each component. We then use this to create both a vulnerability and resource score to assess the risk level of different neighborhoods. We appreciate your time. Thank you for listening to our presentation.
Can you say again, what were your key items that affected things the most when you did the PCA? I couldn't see very well, that one slide. Yeah, maybe, yes, probably vulnerability, I think. Homes built, the dates that homes were built. Yeah, it's mostly that. Is there anything I'm missing? Anyway, what would you say more about this?
The most important ones were homes built in 2010 or later, and homes built in 1950 or earlier.
And can you also do the next slide?
Yeah. So for the resource score, the most important were median household income in dollars and households with no vehicles.
Were there any surprises, actually in general, were there any surprises from any of the results? Sorry, were there any surprises for any of the results that you found through the whole research endeavor?
Most of it was largely intuitive. With the homes, when we were like estimating their affected temperatures due to the heat waves, we saw that like a lot of the temperatures were expected kind of. In apartments, you would see like higher temperatures because they aren't really an isolated unit, whereas like older buildings would have a lot more vulnerability as well due to like poor insulation, yeah.
I got a little confused about where these vulnerability scores weights came from. Like, what part of the data incorporated heat waves? Like, if I had said, is this neighborhood vulnerable to a traffic jam, or is this neighborhood vulnerable to a sharp increase in home prices? Would your method here have output different vulnerability scores?
Could you rephrase that last part? I'm so sorry.
Like, I think I'm missing, I know you did PCA,
Yes.
but it seems like you did it on data that was data about the neighborhoods, but I was missing where the data on heat, like the information about the fact that we care about heat waves came in. Like, if I had asked you to give a vulnerability score to what neighborhood is most vulnerable to have a spike in home prices, I would think I would get different neighborhoods out, but I'm not sure how that would change the output of the model here.
Yeah, Billy, go back a slide. So these factors were what we used in question 1 to determine the temperature. A lot of these were similar. So what we did was we got the eigenvectors and using PCA, we basically here. You got it.
Okay, so the insulation is important to determining the internal temperature of a house, as we showed in question 1, right? And so these homes with built in different years, you could assume that they would have different levels of insulation from those different years, right? And then you also see the proportion of developed or open space in a neighborhood. That open space will help decrease the overall temperature in the neighborhood if it's populated by green space or by other things like such as that.
Yeah, so I guess I agree that these look reasonable afterwards, right? Like, I agree that like insulation affects heat waves and the proportion of developed open space does, but it seems like the methodology used to get these scores didn't know that the problem was about heat waves. If it had been about traffic jams in something that insulation doesn't have an impact on, it seems like you would have gotten the same scores. Or maybe I misunderstood the methodology a little bit. Yeah.
We used the provided data given from you guys for the vulnerabilities, and we...
Oh, you use the...
Yeah, so these data were the same ones we used in the question 1 that are provided. All of these were like already provided to us. And to your point,
you mean this environmental vulnerability? What provided data exactly?
the one provided by like the Envy Challenge, which we use these to like the different statistics about like the homes and their insulation. And I guess to your point about like using these factors for traffic, yes, we will get the same score. But if you're considering about determining a traffic score, we don't think it will be logical to have information about homes necessarily. And in that case, you'll more use factors that are already related to traffic and not that already related somehow and not
Sure.
more about the homes.
Okay, great, makes sense. Thank you.
I had a question about, in the paper itself, you talk about your power due to conduction incorporates the solar power. I was wondering if you could talk a little bit about that and how you came
So
about that.
essentially, for Newton's law of cooling, we calculate like the amount of outdoor temperature, like how that affects the indoor temperature. And part of that considers what we interpret it as is the literal solar radiation. So like the area and the literal like sunniness that the house is exposed to. Make sense?
So how's that going to be incorporated in this term that is the differences in the temperatures?
So we have this TSA variable, which is like solar radiation as well as the outdoor temperature. So we would calculate the effect of the shadiness within the solar temperature, the TSA variable. Does that clarify it? Can I like explain it more or?
Well, in the paper itself, you said that, okay, I'm misunderstanding then. Okay.
Does that clarify anything?
Yes, thank you.
My question is about part 2. You mentioned electrical consumption patterns in Memphis will likely have changed. Climate change, population growth, technological advances. How could you modify your model to adjust to those changes?
Okay, so to adjust our model for temperature changes, we would just simply adjust the heat wave data that we were training it on, that we used to calculate the overall power. If we wanted to change the population, we could probably find the ratio of population to number of dwellings, and then we could then scale our simulation to increase the number of dwellings that we're calculating. And I'm sorry, what were the other ones you asked?
Technological evolution, like electrical vehicles, for example, energy efficient appliances.
Okay, so for that, we could simply just change, we would modify the coefficient of performance for AC units, because that could, as AC unit technology increases, you would expect the amount of energy required for it to cool the house down would decrease, which would then bring the overall power required down. Does that answer your question?
Yeah, absolutely. Thank you.
Great, thanks, guys. Yeah, if you want to do any thank yous for anyone, you can do it now.
I would love to do some thank yous. First, I would love to say thank you to Jane Street for hosting such an amazing event. And thank you to SciAm for giving us the opportunity to present our solution to everyone here. My team and I are incredibly grateful to all our friends and family who have been supporting us, and particular thanks to the Flint Hill Math and Science departments for really making this possible. And last but most certainly not least, the biggest thanks to our coach, the wonderful Miss Van Leeshow, for spending so much time in her last year before retirement, helping us do what we couldn't have done without her. And thank you to Mr. Weeks for being here with us and making multivariable calculus really fun.